Do you stay up late at night thinking about how you can launch a clown out of a cannon? Do you worry that once that clown lands, the energy from the collision with the ground will shake the earth? Do you worry if your cannon is cartoony enough? Will your clown actually fit inside the cannon? Do you worry that the new J.J. Abrams Star Trek timeline might be considered canon? In all seriousness, clown launching is a very, very important topic. And this video is going to attempt to explain the basics behind projectile motion, specifically using the concept of clown launching. Only a few clowns were harmed in the making of this video. Okay, so in order to launch the clown or use the cannon at all, what we really need is some form of energy inside of the cannon. And so what we normally see inside of a cannon is there's some form of explosive, some kind of a gunpowder that's in here, and then the cannonball would be kind of lodged in the cannon so that no air can escape on either side of the cannonball. And then once this was ignited, the gases would expand in here rapidly and force the cannonball out of the cannon. Whenever you go to a circus or you've seen a clown being launched out of a cannon on TV, there's probably actually a giant either compressed air mechanism inside or maybe even like a giant spring type of thing that would shoot the clown out. And then there's always some airbag or some other device that goes ahead and catches the clown on the other side. When we were kids, we used to make potato cannons. Don't do this at home, but in the Boy Scouts we would PVC, and we would use hairspray and shoot a potato out of the cannon. And we, it wasn't safe, but the adults did it with us, and it was a very controlled thing. It was kind of cool. And there's actually a sport to throwing stuff called pumpkin chunkin'. So actually in New Jersey and upstate New York, people build giant devices for shooting pumpkins across large fields because they have nothing better to do. Calculating these things, we need to keep the couple things in mind. We need to make sure that the projectile leaves exactly at the origin of the graph. So you're going to want to set the projectile up at the origin. This means that the cannon will sort of look like it's below the ground. But if the cannon was on the ground, the projectile doesn't leave from the ground, right? Anytime we throw something in the air with force, is going to go up in the air, and it's going to land somewhere downrange. None of these problems will consider friction. None of them will consider wind resistance. All of these are going to be in perfect physics land, which is a new theme park we should start. We should talk. A reminder that all objects are going to travel in two directions, right? So X and Y are independent of each other. The object appears to go through a parabolic motion, but it's actually moving up at the same time that it's moving over. And remember that acceleration is only affecting the projectile in the Y direction and not the X direction. The angle of the cannon will also play a part here. If the cannon is angled in a... well, not downward, that would kill the clown instantly. The cannon is angled over, the projectile won't go very far. If the cannon is pointed straight up, the projectile will just go straight up and fall back down. There actually is an ideal angle for the maximum range, and that is, of course, our favorite angle of 45 degrees. Will give us the maximum amount of up while giving us the maximum amount of over. If we want to throw the projectile really far downrange, we got to use 45 degrees. Otherwise, if we're at 46 or to 90, anywhere from 46 to 90, the projectile will do more up than over. And if we're anywhere under 45, it will do more over than up. So in order to get a nice, comfortable balance, we want to be able to shoot that at 45 degrees. Projectiles leave their cannons. They go up in the air. They're robbed by gravity the entire time that they're flying through the air, and the projectile eventually leaves the ground. So whatever up portion of the projectile gets, whatever up velocity it gets, is constantly robbed by 9.81. And so that results in the object going up and coming down at the same rate, which means that all parabolic flight is technically mirror image. So whatever it does from the beginning of its flight to the very middle of its flight is duplicated on the other side, just in reverse. So the projectile leaves the cannon, goes up in the air. At some point in the top of its flight, the y velocity runs out. The projectile returns to the earth. with the same velocity and the same crash angle. Let's do an example. Let's say I shoot a clown out of a cannon with an angle of 45 degrees. The most efficient angle. And he has an upward velocity of 10 meters a second and an over velocity of 10 meters per second. Well, the Earth is going to rob him of negative 9.81 meters per second. Negative 9.81 meters per second every second, right? So if he starts with roughly 10, he's going to fly up for about 1 second until he runs out of energy. And then he's going to fly down for about 1 second. The projectile leaves the cannon. It goes up in the air. At a certain point, the y velocity is equal to 0. And then gravity starts to pull the object back down. And then the object will crash, right? And these will become mirror images of each other. Right? So whatever happens on the left always winds up happening on the right, provided that the object lands on the same level that it was launched from. Now, in reality, there's a huge problem with this. The Earth isn't flat. Or at least that's what NASA would want you to believe. Really, the Earth is round. So, like in most high school physics examples, what you'll see is that, the object leaves a flat ground and it lands on flat ground, but in reality, the Earth has a curvature. And so all of the math we're doing here is complete. Not really. You just have to take into account the curvature of the Earth. You also have to take into account wind and the density of the air, like the shape of the projectile, the mass of the projectile. There's so many things that you would have to take into account in order to calculate actual projectile motion. But as with most things in the first level high school, most basic version of the most basic version of Newtonian physics that we cover in this very basic class of basicity, we will not be covering all of those extended things. That's something that if you really love science, you'll get to in college, and pretty much any science major does. Okay, to recap here, if I'm just going to draw it all out for you. You have a projectile that is launched from some sort of a cannon. That projectile goes up in the air, and then it comes back down and it lands. As long as those projectile and the cannon are on the same level, the motion going up will be the same as the motion going down. All right, at the beginning, you need to know some information. You need to know the angle of the projectile, and you need to know the velocity that it's leaving the cannon. And then from there, you're going to use trig to break that up into its x component and its y component. And once you calculate that, you'll be able to calculate how much energy is being directed in the up direction and how much energy is being directed in the over direction. In the example that I gave, I said that it had 10 meters per second y and 10 meters per second x, and gravity robs all things of about 9 meters per second. So this projectile would be flying through the air for about 2 seconds, because it would take about a second to go up until this 10 was robbed by 9.81 and then was equal to 0, and then the object would start to fall back down. Once it crashed, it would land at the same angle, doing the same speed as it was launched at in both the x and y direction, provided it landed on the same plane. And because it flew through the air for 2 seconds at a velocity x of 10 meters per second, it would have done about 20 meters downrange. Okay, and you can use the kinematics formulas listed here to calculate everything that you need to know. Just a reminder that you may want to make sure that you have like little boxes in your notebook that say, hey, this is all my y stuff, and then over here, this is all my x stuff. And then when you're using these formulas, you keep all your x stuff on one side, all your y stuff on the other, and you calculate everything using these little sub x's and sub y's, just so you know that you are not mixing everything up. These motions are independent of each other. I mean, they look like they are together, and they do work together, but as physicists, we need to separate them in order to calculate them.